In this lecture, we shall see how to measure the efficiency of algorithms. We are very interested in measuring the performance of algorithms. Specifically, we want to bound the running time or the memory usage of the computer. Memory is also known as space. An important point is that these quantities, the time and memory, are measured as a function of the input length. Doesn't make sense to give them absolute quantities like 17 or 15, but they need to be a function of the input length. This makes sense because the longer the input, the longer it takes for the computer to just read the input, and most natural problems will require an algorithm for them to at least read the entire input. The input length is usually denoted with the letter n. Hence, we're naturally interested in which functions of n grow faster than others. Let's consider the following picture, which has some of the popular functions drawn on it. On the x-axis, we can put the input length. And on the y-axis, we can put the running time, or the number of steps that an algorithm takes on the corresponding input length. Now note that the scale on the x-axis and on the y-axis is not the same. The x-axis goes all the way to 900, and while the y-axis goes all the way to 18,000. Okay? But I've drawn the picture this way so that we get a more meaningful picture. Okay, the first function that we see is n, okay? And because of the different scale, this looks like a nearly horizontal line. Then we see n log n, then we see n log square n, and these two functions are fairly similar to n in terms of growth, although they grow faster. Then we see n raised to a power larger than 1, specifically n to the 1.5, and this already starts to grow a lot faster. Then we see n squared, and then we see an exponential function like through the n, which looks almost like a completely straight vertical line on the slide. Okay, let's see what this thing means. Okay, so let's consider, for example, that you have an input of length n 700. So you're right here. Well, if you use an algorithm that runs in time n, okay, the time that you take is this, which we can take to be maybe 1 hour. If you use an algorithm which runs in time n log n, then the running time would be this, which we can take to be approximately 2 hours. If you take n log square n, then it will take about 6 hours. While if you use an algorithm which takes n to the 1.5 time, it will take something like 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, about 18 hours, so almost a day. If you use an algorithm which runs in time n squared, then the time isn't even shown on the picture, is up there in the sky. It will probably be extremely large, something that you cannot wait for. Not to talk about a function like through the n, it would have a completely astronomical time, which would be completely impractical. So as you can see, the running time of the algorithm is absolutely critical on whether you can actually get an answer in a reasonable amount of time or not. You may be willing to wait an hour, but not 18 hours, not to talk about days or weeks. So the exact time of the algorithm, however, depends on the actual machine. So we want to have a robust theory, so we are going to ignore constant factors as much as possible to have a theory which applies to most computers. For example, if I have an algorithm that on my computer takes 67n plus 15 operations, well, it's about the same as what may take on a different machine, say 58n minus 15 operations. The difference between these two quantities is not very important for me, because if tomorrow there is a new processor which is a little bit faster, the difference will be blurred. So we'd like to think of these two quantities as being essentially the same. And now we're going to give definitions that make this precise. Okay, the first definition that we give is that of big O. So here we have two functions, f and g, and we're going to say that f of n is big O of g of n if there are two constants, c and n sub 0, such that f of n is always at most c times g of n whenever n is larger than n0. Okay? And the meaning is that f grows no faster than g up to some constant factors. Okay, we can have an example of this. For example, the function g could look like this. And the function f could be something like this. Now, we claim that f is big O of g of n, and that's because if you look at the function 2 times g, then indeed it is true that f is always less than 2 times g, wherever n is bigger than some initial n sub 0, which we can take to be this value here. This can be n sub 0, and in this example, c would be 2. Okay, let's see some more examples. For example, we can ask ourselves if 5n plus 2n squared plus log n is big O of n squared. And the answer is yes. Now, which value c can we take? Well, I'm tempted to take exactly 2, c equals 2, but it wouldn't quite work, okay, because I also need to account for the 5n and the log n. So a simple value that works is equal to 3. And indeed, for large enough n, you have that 5n plus log n is less than n squared. So overall, you have an n squared from here and 2n squared from there. So the sum will be at most 3 times n squared. And in fact, you can pick any c larger than 2 and adjust the constant n sub 0 accordingly. As another example, we can ask ourselves if 100 times n squared is big O of true the n. And again, the answer is yes. And we can pick c to be equal to 1. In fact, any c larger than 0 would work for large enough n. And this just reflects the fact that the exponential function grows faster than any polynomial. Yet another example, we can ask ourselves if n squared log n is big O of n squared. And here the answer is no. N squared log n is not big O of n squared. So what does that mean in terms of our constants c and n0? It means that in fact for every possible choice of c and n0, you can find an n which is larger than n0, such that n squared log n would be larger than cn squared. And in fact, if you fix c and n0, it suffices to take n larger than 2 to the c, in which case the quantity n squared log n would be larger than n squared c. So display with quantifiers is not of critical importance for us. It will not be really a focus of this class, but I want to give a sense of what's behind an assertion that f of n is big O of g of n, and an assertion that f of n is not big O of g of n. Let's do yet another example. Is true the n big O of true the n over 2? And the answer again is negative. No matter which constant c and n0 you take, I can find an n which is larger than n0, such that true the n would be larger than c times true the n over 2. Okay? In fact, it's sufficient to take any n that's larger than 2 log c, and to view that you would have this inequality here, you can notice that true the n is equal to true the n over 2 times true the n over 2. Now, for this choice of n, one factor true the n over 2 would be at least c, and then you prove this inequality here. Okay, let's see some other examples. Let's start with first one. Is n log n big O of n squared? Well, the answer is yes, because the factor log n here grows less than another factor of n on the right. Let's go to the second line. Is n squared big O of n to the 1.5 log 10n? Okay, and the answer here is no. On the left, I have a larger polynomial, so it doesn't matter that I have this log factor here, and square will grow faster still. So they're not. Let's go to the third line. Is true the n big O of n to the very large constant? And the answer again is no. Exponential function grows faster than any polynomial. Let's go to the fourth line. Is square root 2 raised to the power log n big O of n to the 1/3? Well, to answer this question, it's convenient to do some manipulation. Okay, we can see that square root 2 raised to the power log n is equal to n to the half. Okay, and n to the half is not big O of n to the 1/3. Okay, this is a larger polynomial. Half is larger than 1/3. Hence, square root 2 to the power log n is not big O of n to the 1/3. Next, we ask if n to the log n is big O of log n quantity to the log n. And here again, it's convenient to do some manipulation. We can notice that n to the log n can be written as 2 raised to log n times log n, which if I now take this 2 and this log n here, I notice that the 2 to the log n becomes log n. So this quantity here is equal to log n to the log n. So these two quantities are actually equal, and hence the left-hand side is big O of the right-hand side. Let's move to true dn equal to big O of 4 log n. Well, again, we can do some manipulation here. We can see that the 4 to the log n is actually 2 raised to the 2 log n, while true dn can be written as 2 raised to 2 to the log n. So clearly the 2 to the log n in the exponent is a lot faster than 2 times log n. Hence, the left-hand side is not big O of the right-hand side. In the next one, we ask if n factorial is big O of true dn. And you should recall that n factorial is the product n times n minus 1 times n minus 2 times all the way to 1. Okay? And answering this question is not immediate. Perhaps we can resort to some known estimates. So it's known that n factorial is fairly close to n over e raised to the power n, where e is the important quantity 2.781 dot dot dot. Okay, specifically it's known that n factorial is at least n over e to the n times 2.5 square root n, and it's at most it's most 2.8 times square root n over e to the n. So looking at this, we can realize that n factorial is not big O of true the n. On the other hand, we can see that n factorial is big O of n to the n. Finally, we can ask if n times true the n is big O of true the n log n. And here again, we can do some manipulation. We can see that n times true the n can be written as true the n log n plus n. So here you have true the log n plus n, while on the right hand side you have true the n times log n. So clearly the times grows faster and the big O is satisfied. Okay, so these were some examples with big O. Let's now move on to something else. Okay, the corresponding lower bound to big O is what's called the big omega, okay, which is denoted with the Greek capital letter omega. Okay, so we say that f of n is big omega of g of n. Again, if you can find some constants at c and n0, such that when n grows larger than n0, f of n will be at least c times g of n. And the meaning is that f grows no slower than g up to constant factors. The first example, we can ask if 0.01n is omega of log n, and the answer is yes. This is a polynomial function which will definitely grow faster than logarithmic function. And just to verify that, we can notice that you can pick any value for c that's larger than 0. Another example is n squared over 100 omega of n log n. And the answer is again yes. Here I have a polynomial that's larger than 1, and that's gonna grow faster than n times log n. And in fact, again, you can pick any c. If you want to make things simple, you can pick c to be 1 over 100 to exactly cancel this constant, but you don't have to. Let's now go to a third example. Is square root n omega of n over 100? And the answer is no. The left-hand side is a polynomial is n raised to half, while the right-hand side is n raised to 1. Okay, multiplied by constant, but the higher power will count a lot more. So the answer is no in this case. Fourth example is n to the n over 2 omega of true the n. The answer is no. Again, for every c and n0, you can find an n that's larger than n0, such that the 2 to the n over 2 is less than c times 2 to the n. Okay, the big omega and big O notation are two sides of the same coin. We can note that a function f is a big omega of g of n, if and only if the function g of n is big O of f of n. Okay, and similarly, f of n is big O of g of n if and only if g of n is big omega of f of n. So, for example, 10 log n is big O of n is the same thing as n is a big omega of 10 log n. 5 of n, 5n is big O of n, and n is big omega of 5n. Okay, if you have them both, then you get to theta. So that's another very important notation in algorithms. We say that f is theta of g of n. Again, if you can find a constant n0 and now two constants c1 and c2, such that for every n larger than n0, f of n is less than c1 times gn, and gn is less than c2 times f of n. The meaning is that f grows like g, both in upper and lower bound, up to constant factors. For example, we can ask if n is theta of n plus log n, and the answer is yes. This extra summed log n will not change the asymptotics. So what are the constants C1, C2, and N0 that satisfy our definition? Well, we can take, for example, 1 for C1, okay? This will ensure that n is at most 1 times n plus log n, which is obvious. And for C2, we can take 2. And this will ensure that n plus log n is at most 2n, which is again obvious. The important thing to note is that f of n is theta of g of n if and only if f of n is omega of g of n, and at the same time f of n is big O of g of n. Okay, so theta is just saying that both big O and omega hold, and from this and the previous equivalencies, you can also verify that f of n is theta of g of n if and only if g of n is theta of f of n. Okay, so we have seen a lot of examples, and we went very slow. Now we want to get some intuition about these things and not really have to be too bogged down with these constants and quantifiers. In particular, we are going to mix things up. We're going to see sometimes big O, theta, and other things in the middle of equations. Okay, we're going to see expressions like um, n plus order of log n is order of n. Okay, and something like this means that whatever constant c you put here, you can find another constant c here that makes things hold. Okay, for every constant c here, you can find a constant c prime here, so that when n becomes large enough, larger than n sub 0, you have that n plus c log n is at most c prime n. Okay? You will also see the use of big O in the exponent. For example, n cubed log n is n to the big O1. Okay? Big O1 just means some constant. This means that you can find some constant and some n0, such that when n becomes large enough, larger than n0, n cubed log n will be at most n to the c. Okay, and for this, for example, you can take c equal to 4. And you will also see things like 2 to the n plus n to the big O1 is equal to theta of 2 to the n. What does this thing mean? It means that no matter which constant c you put for the big O1, okay, you can find two constants c1 and c2 for the definition of theta, such that the quantity 2 to the n plus n to the c, okay, is sandwiched between c2 through the n and c1 through the n.